This is an example of anti-deriving using the power rule. This rule is exactly reverse of the derivative power rule. This is the natural log antiderivative rule, and again, it is exactly opposite of the natural log derivative. This is an example of the exponential antiderivative rule, which conveniently is exactly the same as the derivative rule. This is the exponential with a constant antiderivative rule, very similar to the derivative rule. However, instead of multiplying by the constant in the exponent, you are dividing by the constant. And last but not least is the constant rule, probably the easiest and most forgotten rule for anti-deriving.
This is a very simple example of anti-deriving using a couple of the rules that we have learned, including the power rule twice and the constant rule. As you can see, I'm adding 1 to the exponent and then dividing by that new exponent for both the x squared term and the negative 6x term. And then the plus 17 will be multiplied by x using the constant rule. So the simplified answer for this antiderivative is x to the third over 3 minus 3x squared plus 17x, and then don't forget the c on the end. And here is another antiderivative using a couple of the simple rules such as the power rule and the natural log rule. This is an example of an anti-deriving using the substitution rule, where we take the more complicated section of the function and substitute w in, so that way we can use our far easier power rules and our standard anti-deriving rules. In this situation, when you derive dw with respect to dx, you get 1. So dw does equal dx in this case. So when you plug dw in for dx, you just get dw. So it's w to the third power, dw, and you use your standard rules that you've learned earlier in the unit to anti-derive. And then once you reach the end, you plug your w back in. This is another example of a substitution problem where you plug w in for the more complicated part of the problem and then derive, in this case, w with respect to dt, and then you plug your dw over 3t squared back into the equation for your antiderivative, so that way you can solve with respect to dw. This example shows you how you can use the fundamental theorem of calculus to evaluate a definite integral with bounded regions, similar to how you would use a calculator, but this way your answer will be far more accurate and precise. This is the equation that you will need to antiderive using the integration by parts method. Integration by parts kind of reminds me of deriving using the product rule, simply because you are using two different functions in the integration process. Simply determine which terms will be the u term or the v term, so that way you can plug all of your information into the integration by parts formula to give you your antiderivative.